Chapter 4, Section 4.3, the atom. Now we'll talk a little bit about the history of the atom, specifically how we found some of these subatomic particles. And this is some pretty cool stuff, the experiments are. So I would suggest getting on YouTube and looking up some other background material on this stuff. But I'm going to point out the most important stuff to know and to remember. All right, so the first little thing we need to talk about is just Dalton's atomic theory. Now, Dalton's atomic theory sets up, and chemistry is based off of this theory. Okay, and it was the first time the idea of an atom was put on paper. They had the idea of the atom up until this point, and they operated as if atoms existed, but John Dalton was the first one to say, hey, atoms exist. And here are his postulates, here are his ideas of the atomic theory. Now remember what a theory is. A theory explains how or why something happens. Okay? So the four ideas in your text behind Dalton's atomic theory is everything is made of atoms. So all matter is made of atoms. And it's the smallest, the atom is the smallest part of an element that looks like that element. So for instance, copper, a copper atom is as small as you can get to still look like copper. As soon as you start pulling apart that copper atom, it no longer looks like a copper atom. Now it's just a bunch of protons, neutrons, and electrons. So Dalton went on to say that all atoms of a given element are identical to one another and different from atoms of other elements. Now we know that they're not all identical, but what he's saying is that a copper atom looks like copper and an aluminum atom looks like aluminum, but a copper does not look like aluminum. He defined compounds, atoms of two or more different elements combined to form compounds. And then he also went on to say that a particular compound is always made up of the same kinds of atoms and the same number of each kind of atom. And this gets back to the law of law of definite composition, or law of definite proportions. And that is, the same thing that we talked about earlier. Calcium carbonate is always made up of one calcium, one carbon, and 3 oxygens. And then finally, he went on to say that a chemical reaction involves the rearrangement, separation of, or combination of atoms. Atoms are neither created nor destroyed. And that comes from the idea of the law of conservation of mass. So you know about conservation laws. You learn that that charge is conserved. In this case, mass is conserved. So Dalton came up with the basic idea of the atom and laid down some basic rules for atoms. A little bit later on, a guy named J.J. Thompson discovered the electron. And he did this by using a cathode ray tube. So what he did, and again, you can look up experiments of this. There are actual videos of cathode ray tubes. He had a tube, and in that tube, he took out all or most of the gas. So he evacuated the tube. So there's just a few atoms of a certain element in there, right? And then he could hook that tube up to electricity, right? And what he found was that when he hooked this up to electricity, there was a beam of light that would always flow from negative to positive. So he did a couple experiments with this. First experiment he did is right here. He took a positive electrode, so here's an electrode that's positively charged. He took a negative electrode, so again an electrode that's negatively charged. And what he found was that this light, this supposed light, would bend toward the positive. Well, you can't bend light with a positive and negative plate. So already he's thinking, nah, this can't be light. This has to be something else. So he did another experiment. He took and put like a chunk of metal in here. So he put a piece of metal in here that could move. So this metal, let me blow this up out here. So this metal could flop over. So if something hits it, it would just flop over like that. All right. So he did that, turned it on, and sure enough, when the light, quote unquote light, hit it, the metal flopped over. Like that. And he also had a spinning wheel in there. So like a paddle wheel, like for a steamboat. And what he found, and he put that on rails, and he found that again this light would cause it to move. And light doesn't do that. Light doesn't cause things to move like that. So that's how he came up with the idea that this has to be a particle. Now, he named that particle the electron. He also figured out that all matter has these electrons in it because he used several different types of gases in this tube, and they all exhibited the same behavior. He figured out that it was negative because it was attracted to a positive plate, and it always would flow from negative to positive. So again, attracted to the positive. And then Thompson came up with what's called the plum pudding model. And here's an idea of the plum pudding model. And all it is that we have these negative electrons. So here are all these electrons. And those electrons are floating in a positive cloud. And that was his idea of the atom. So he said the atom is almost entirely empty space. Then comes along Ernest Rutherford. And Rutherford conducted what's called the gold foil experiment. Now this is a pretty neat experiment. Basically, by Rutherford coming along, they knew that the electron had basically no mass. So the electron is basically massless compared to the rest. So if that's true, and if Thompson's plum pudding model is true, then what should happen is if they shoot a pretty big particle at this atom, then the pretty big particle should go straight through. Why? Because Thompson said the atom was mainly a positive cloud that had these relatively massless electrons in them. So imagine throwing a bowling ball at matches. Those matches aren't necessarily going to make the bowling ball move if the matches are just hanging up. The bowling ball is just going to plow right through them. And so that's what Rutherford set up. So here's his experiment. He had a lead container, and inside that lead container there is a radioactive source. So there's a radioactive source of particles. And that radioactive source gave off alpha particles. Now, alpha particles are basically helium atoms, just the nucleus though, no electrons. So that's how we get this 2+ charge there. So they had it to where it would come straight out, so the alpha particles would come straight out, and then they would hit a piece of gold foil. Now they used gold because you can pound it real thin. Here you can see this is just 3 atoms thick, and you can pound it that thin. You can pound it so thin that you can see through that gold foil. That's why they used gold. So what should have happened is these alpha particles should have, and I'm back up here, these alpha particles should go straight through, right? Because the alpha particle is huge, it's the bowling ball. They think the atom has basically nothing in it but electrons, which are relatively massless. And that's what they saw. They saw that most of them went straight through, but not all of them. A small percentage of them were deflected. So they came out at different angles. And an even smaller percentage of them bounced straight back, or nearly straight back. So what Rutherford figured out was there must be something in the middle of that atom. Okay, so here's my alpha particle coming through. That's fine. Here's my alpha particle coming through. That's fine. Now here's another alpha particle coming through. Oh, too close to the nucleus. It gets deflected away. So we said that it had to be something small and dense. Small because most of the atoms went straight through, right? If it was big, if this nucleus was big, so let me draw another atom here, and if this nucleus were big like that, then most of the alpha particles would be deflected away. Right? That's how they knew that it had to be small, like really small. Dense It has to be dense because, well, first of all, it's really small, but the alpha particle is huge. So since it's making the alpha particle move, it must be something that's pretty solid, so very dense. And so that's how they came up with the idea of the nucleus. We know now the nucleus contains the protons and neutrons. Protons were discovered again using the cathode ray tube. What they saw was that, yes, the electrons came out this way, but the protons were going backwards, the opposite way, attracted to the negative. And then a guy named Chadwick came up with the idea of the neutron, which is pretty hard to find because the neutron is neutral. So the atom is made up of a proton, a neutron, and an electron, most atoms. The symbol for a proton, we use P+. Symbol for a neutron, we use N0. Symbol for an electron, we use E with a -1. The charge of a proton is +1. The charge of a neutron is 0. The charge of an electron is -1. Now that's the relative charge. That's not the actual charge. So in other words, the proton and electron have about the same charge, but opposite. The neutron has no charge. It's neutrally charged is what we should say. It's made up of charged particles that cancel each other out. The neutron is. Now, relative mass. The relative mass of a proton is 1. Relative mass of a neutron is 1. The relative mass of an electron is 0. So you can remember this, or really what you need is that it's 0. And then location. The proton and neutron, to say that it's located in the nucleus is wrong, because the protons and the neutrons are the nucleus. A lot of times there's a misconception that inside the atom there's this thing called the nucleus, and then the protons and neutrons live inside that thing. Well, that's not what happens. Here's the atom. Proton, 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 neutron, neutron, neutron. That is the nucleus. Much smaller, of course, but I can only draw so small. Okay. Now this is important information. Looking up and understanding this background material, and you might also want to look up and read about the Millikan oil drop experiment, because it's a big one too.